Hi viewers, welcome to my channel. In the present class, now I am going to discuss the topic longitudinal vibrations in a bar which is free at both ends. Right. In the previous class, we discussed the longitudinal vibrations in the bar clamped at both ends. Okay. Here we discuss the vibrational modes, the longitudinal vibrational modes in a bar which is free at both ends. Right. Let us consider a rod of length L, which is free at both ends, right? According to the boundary condition, because the both ends are free, the first end x is equal to 0. At x is equal to 0, there antinode will get some. That's why the displacement would be maximum. Since y equal to y max, dou y by dou x is equal to 0. Similarly, at the second end also free end here we are taking. At x is equal to L, here also the displacement of the particle, vibrating particle will be maximum, so that dou y by dou x is equal to 0. So finally, what I am saying is at x is equal to 0, dou y by dou x is equal to 0. This is one boundary condition. At x is equal to L, here also dou y by dou x is equal to 0. So these two boundary conditions we are using in this present discussion. Okay, so that is keep in your mind. Let us move for the derivation, sir. Yes. So dou y by dou x equal to 0 at x is equal to 0 and x is equal to L. So what is the general expression for the superposed wave y equal to a e power j into omega t minus kx plus b e power j into omega t plus kx. This is the general equation, general solution of the longitudinal wave equation. Okay, now differentiating this equation with respect to x, dou y by dou x is equal to a e power j into omega t minus kx, same a into e power j into omega t minus kx. Okay, kx into again dou by dou x of minus kx, you will get minus kx, j multiplied inside, minus jk comes plus. Similarly, for the second term, b e power j into omega t plus kx, again dou by dou x of j into k jk. Okay, sir, this is something equation. Now let us apply the boundary condition, the first boundary condition. At x is equal to 0, what we have the boundary condition? Dou y by dou x equal to 0. So in this you substitute x is equal to 0. Got my point, sir? X is equal to 0, you have to substitute here. Then dou y by dou x is equal, right? Jk minus jk a e power j omega t plus jk b e power j omega t. Right, sir? Now jk taking common, minus a e power j omega t plus b e power j omega t. Okay. So here dou y by dou x equal to 0. So this RHS side, that is equating to the 0. Then again you take the common here, e power j omega t. Okay. Then jk minus k plus b e power j omega t is equal to 0. There jk not equal to 0, e power j omega t not equals to 0. Then minus a plus b must be equal to 0, a equal to b. Substitute this value in the equation, general solution equation. Y equal to, we get a e power j into omega t minus kx plus b replaced by a, hence a e power j into omega t plus kx. So in these two terms, you can take the common a e power j omega t. In the first term, e power minus jkx left plus the second term e power jkx left. Right, sir? But e power minus jkx, e power minus j theta equal cos theta minus j sin theta. E power j theta equal cos theta plus j sin theta. Okay, so using that formula, e power minus jkx plus e power jkx is equal to 2 cos kx you will get. Imaginary terms cancel, only the real parts adding, that gives 2 cos kx. That's why putting this value here, then we can write y equal to a e power j omega t into 2 cos kx, 2 cos kx. So this is the y terms, y equal to, we got that one, right? Now, uh, so let us take the differentiation of that. Let us take the differentiation of that. So what we get, y, dou y by dou x is equal to minus 2a k e power j omega t sin kx. Right, sir? Here, let us apply the second boundary condition. What is the second boundary condition? At the second end of the bar is also free end. Here, both ends are free ends. At x is equal to 0, particle displacement maximum, hence dou y by dou x equal to 0. Second end position, x is equal to L, because we have taken the rod of length L. That's why at the second end, the position is x is equal to L. There the particle vibration is maximum. Hence dou y by dou x equal to 0. Then you equate this to 0. Then a not equal to 0, k not equal to 0, a for g not k not equal to 0. That's why must sin kl should be equals to 0. Kl is equal to n pi. Sin theta equal to 0. This is possible for when theta equal to n pi, because sine 0, sine 2 pi, sine 2 pi, sine 3 pi, sine 4 pi, and so on 0. And kl equal to n pi, where n values so 0, 1, 2, 3, and so on. So let us consider nth mode of vibration. For nth mode of vibration, we are writing case as kn, k subscript n, l equal to n pi. From this kn is equal to n pi by n, n pi by l. This is some equation number. What is k here? K, wave constant, propagation constant. K related with angular frequency and velocity of the wave, longitudinal wave, omega by c. But omega is equal to, that is 2 pi times to the frequency, 2 pi fn, 2 pi f, because nth mode of vibration, we are writing 2 pi fn by c, by c. You substitute that value here, sir. Then 2 pi fn, okay, by c is equal to into L is equal to right side n pi. Right, sir. Pi cancel. From this, fn is equal to the frequency of nth mode of vibration. Fn is equal to, taking cross multiplication, will get nc by 2L. Same formula. We got the same formula in the case of rod clamped at both ends. This represents the frequency of nth mode of vibration. The rod is in the nth mode of vibration, then the corresponding vibrational frequency formula Fn equal nc by 2L, where n represents the number of mode. If n is equal to 1, that shows fundamental frequency. So what you get, when n equal to 1 substituted, F1 equal to c by 2L, that is called fundamental frequency. If n equal to 2, we'll get F2 is equal to 2c by 2L, right? 2c by 2L. 2c by 2L. That is 2 times to the fundamental frequency. You see here, Fn equal to nc by 2L. That equal to n by 2L. But see the velocity of longitudinal wave in the rod. That formula we know root of y by rho. So that is substituted here. Okay, n by 2L root of y by rho. In this, n is equal to 1 substituted. Then we get F1 equal 1 by 12 root of 5 by rho. This is the fundamental frequency. F1 equal to c by 12, where c value is substituted, simple, root of 5 by rho. This is the fundamental frequency of the rod. With rod, here 2 ends are free. Next, if n is equal to 2, then F2 equal to 2 by 12 root of 5 by rho. That is called first overtone or second harmonic. First overtone or second harmonic. If n equal to 3 substituted, we get the equation 3 by 12 root of 5 by rho. This is that equal to 3f1, right? This is the second overtone or third harmonic, right, sir? So we can show these modes of vibrations graphically like this. For the fundamental frequency, at both ends we are getting the maximum displacement positions. This is here the particle displacement maximum, here particle displacement maximum. So this represents the fundamental frequency. This is the antinode, node, and anti. Yes, the second thing. So this is what is this? First overtone. First overtone or second harmonic here. Antinode, this is the maximum. Here the particle displacement 0. Here the particle displacement maximum. Here 0. Here maximum. Okay. Next. For the second overtone or third harmonic, that is F3. F3 equal to 3F1. So for that, the corresponding graphical representation or wave representation will be like this. So this is about the vibrational, longitudinal vibrational modes in the rod, which is whose two ends are free at both ends. Okay, whose two ends are free. Okay, thank you.